Hello sir and everyone, welcome to our presentation about assignment control system. My group consists 4 people, myself, Fahmi, Ram, Hirish and Ravin. We will be walking you through the assignment for the control system fundamental course, where we analyze the performance of a unity feedback system with a given forward path transfer function. In this assignment, we are tasked with calculating key performance metrics including the peak time, settling time and percent overshoot for a system with a gain k equal to 40. This value will help us understand the system dynamic behavior. We will also simulate the system response using MATLAB and Simulink with a step input showing how the system reacts over time and comparing the calculated values to the simulated result. Finally, we will calculate the steady state error for different input types such as step, ramp and parabolic. My team will guide you through each step of the process, showing you the MATLAB commands used, the analysis and the conclusion drawn for the result. Let's dive into the details.
Hi sir, my name is Tilakram Analaki Selvaram. My matrix number is B11-231-0569. Today I'll be reviewing the calculation for our control system assignment, which is given by the G1S. So let's have a look on it. So basically our assessment have given a transfer function, which is GS, which is on the numerator K pole, and the denominator is S plus 8.5 and time multiplied with S square plus 3S plus 3.25. So as you can see in the assignment, they have given us a value K equals to 40, which I have substituted over here, and this is my GS transfer function. So in order to attain the error transfer function, I've using this formula, which is G1 over G1S divided with G1 plus G1 over S. So by utilizing this, I'll be attaining the equation of this, which can be summarized into the last equation, which is 40 over S plus 5.5 multiplied with S square plus 6S plus 12.295. So based on this, we can attain that the Wn is equivalent to 3.5 radian per second and the L equals to 0.857. Utilizing both of the information, we can use to find peak time, percent overshoot and also settling time. So first of all, let's find the peak time, which is Tp equivalent to pi over Wn multiplied with square root 1 minus L square, which will be given. The answer for the peak time is 1.67 second. Second will be the percentage of the overshoot, which is percent overshoot equivalent to 100 power of e power of negative ln divided with square root 1 minus L square, which will be given. The final value will be 21.14 percentage. And finally, without further ado, which is settling time, which is we are using 2% criterion. So as you can see, this is the formula for the settling time, which is 4 over LWN, which will provide us the answer of 1.33 second. Next is the system stability analysis. So as you can see, this is the S-plane view plotting for the equation, which is 40 over S plus 8.5 times with S square plus 3S plus 3.25. So you can see there's a conjugation of complex number, which still at the left plane, and also another pole at negative 5.5, which is also at the left plane as well. So as you can see in the system, there is no any pole provided in the right plane of this system. Hence, since all the poles of the system are only available at the left plane, thus the system is considered stable. Next, let's look into the steady state analysis. So when we look into the steady state analysis, first we have to declare the type of the system. Since there is no poles situated at the origin, thus we declare it as type 0 system. Let's look into the calculation of finding the steady state error for step input, ramp input and also parabolic input. So as you can see here, Kp is equivalent to limit as approaching to 0 for GS. This is for the step input. So as you can see, we attain the value of Kp is 1.448. So utilizing the formula 1 over 1 plus Kp, we would attain the steady state error for the step input, which is 0.409. But in percentage, we mentioned that as a 40.09 percentage. So now for the ramp input, let's look into the Kv, which is velocity constant error. So when the S is approaching to 0, so it multiplied with S times with GS. So when I substitute, I attain the value of 0. So when you want to find for the steady state error, it's 1 over Kv, which is we'll get the answer of infinity. Same goes for the parabolic input. So we would like to attain the acceleration constant error. So when limit is approaching s equivalent to 0, approaching to the 0, we attain the acceleration constant error equals to 0, and the steady state error we attain is infinity. So this is for the steady state analysis and the system stability, and also finding the transfer function of the equation for finding the settling time, peak time for the transfer function. So that's all from me, sir. Thank you very much.
Hello everyone, today I'll be presenting for our control system simulation for the given transfer function. So we analyze the system response using this MATLAB simulation and we discuss our findings of this simulation. So this is the block diagram for our simulation assignment, and we place the step input block, sum block, transfer function block, mux, and the scope block. So in this transfer function block we place this, as you can see, this transfer function in this transfer function block. So we straightway go to our comment section. So we already defined the transfer function in this comment section part, and we also declare that our system has a forward path transfer function, and it is as a the k equals to the, which is a numerator, is equals to 40, as well as the transfer function and all that. So later on, we analyze for the step response analyzation. We declare the comment step info, and this comment will show us the peak time, settling time, and the overshoot percentage as well. So later on, it will give the numerical value of the settling time and peak time and overshoot. Well, so the settling time is at 3.1966 seconds, and the overshoot percentage is 21.34%. As for the peak time is at 1.3828 second. So these are the results from our simulation comment over here. So if we refer to the graph, uh, on this is our plot for our step response, and in this plot we can see that the peak time is at 1.38 second with the amplitude of 0.7177, and the response, which is the response is settles at a band of 2%, at around 3.20 seconds. As for the overshoot is, as we can see over here, is at 21.34%, above the steady state value. So later on in the comment section, we straightway go to the we comment that to show that the state space representation, where we convert the transfer function to state space representation using the command tf2ss. So in this comment section, we calculated the steady state error for different inputs, and we found out that the uh, the the step input uh, is this one, 20 221 over 541, which is around 0.4085 value. So in summary, we can say that the system is in stable condition, and but it has a, significant amount of overshoot percentage, and it also settles very quickly around 3.20 seconds, and it can track step input and all that. So these are the output that we get from our simulation, and it match up with our calculation as well. So that's all from me. Thank you.
My name is Avindra Sanlik Prakasam. My metric number is B1123109192. I want to explain about key observation, settling time discrepancy, overhand calculation predicted 1.33 second while MATLAB give 3.9960 second. The largest difference caused because our hand calculation only considered the dominant second order poles, -3 J 1.87, the real pole at 5.58, slower decaling component. The MATLAB settling time calculation includes the effect of the poles peak time difference. The MATLAB value 1.3828 seconds is more accurate than our estimate 1.67 seconds. Our calculation was based on the approximate dominant poles only overshoot agreement. Both methods show overshoot around 18 until 21%. The difference of 3% is reasonable given our approximation. Reverse system understanding the MATLAB result reveals that the system has faster rise time 0.591 second than what our simplified analysis suggests. The actual setting is slower due to the combined effect of the auxiliary component from complex poles, the slower decaying real pole at 5.5. The overshoot is slightly higher than predict but still in reasonable agreement. Recommendation for greater hand calculation to better match MATLAB results. Consider all poles in time reasonable calculation, not dominant poles. No signs charges in both array. Step response settles to finite value. Steady state error validation. The method step response shows final value 0.59, which matches our calculation. Calculate steady state error 40.9%. Final value is 1.448 until 0.591 to matches MATLAB setting value. That's all. Thank you.
To wrap up, we have analyzed the performance of a unity feedback system by calculating key metrics like peak time, settling time, and percent overshoot. Both our analytical calculation and simulation in MATLAB match, confirming our result. We also assess the system stability and confirm that it is stable, as the given value indicate no issues. Additionally, we calculate the steady state error for step, ramp, and parabolic input, helping us understand how the system performs under different conditions. In conclusion, the system behaves as expected, is stable, and shows acceptable performance. Further improvement could be made to enhance the accuracy in tracking higher order input. That's all from us. Thank you for watching.